show you today how to write a software delay using assembly code of PIC microcontroller. Alright, so I have one of the experiment of my course. So the experiment says create an MPLAB project where we have one LED connected to port C, RC0 and RC1, and we use PIC microcontroller 16F877A, and we have a clock frequency of 4 MHz. The delay will be 1 second. So we need to flashlight the LED as on and off between RC0 and RC1, and there is a delay of 1 second between them. So there is an algorithm here describe the code, but I don't think I need it. But anyway, I'll go through back and forth when I write the code. So let's start with the project. Okay, so we need 877A, P16F877. Next, simulator, next. Okay, so let's say software, well, let's call it experiment 3. Finish. All right, we'll just close that. New assembly file, and let's call it software delay. Okay, finish. Okay, so the first thing I need to do is to write the include file as usual. Include p16f877a.inc. Okay, so then we have the org 00, and at the end we have end. Okay, now before we start, we need to calculate the delay. So let me write the delay here, the calculations. So I have 4 MHz. I have frequency of the oscillator is 4 MHz, and I need a delay, or a software delay, let's call it a delay of 1 second. Software delay means that we need to use the instructions, the execution time of the instructions as an accumulative to reach to 1 second. So in order to do that, we need first of all to calculate how much time does it require to execute one instruction. So in order to do that, we need to calculate first the instruction cycle, instruction cycle, which equals to if oscillator divide by 4, which means 4 MHz divide by 4, that's equal 1 MHz. Okay, now the execution times of the instruction, you know that the relationship between the function and the time is 1 over function, 1 over t, and t equal its relationship between time and frequency. So 1 over f. which is in our case the execution time of the instruction is equal 1/1 megahertz. That's 1 microsecond. Okay. Which means each instruction which has one cycle will be executed in 1 microsecond. Okay, good. So now we need to create a delay of 1 second. Let me do it just in let's call it like this. It's a subroutine, and we have a return. Okay, we need to create a subroutine that at the end will produce 1 second. All right, so first thing we need to do is to define an internal loop. This internal loop, but before we do that, let me just calculate one thing. So if I have 1 microsecond for execution time, so the delay will require, so delay is equal C is a constant times 1 microsecond which means 1 second equal constancy times 1 micro. This leads us to C equal 1/1 micro, and this will equal to 1 million. Okay, which means that if I want to have a 1 second delay, I need to execute an instruction for 1 million times. An example instruction like no operation, it's an instruction that executes in 1 cycle, which means it's executed in 1 microsecond. That means I need 1 million no operation in order to execute or to produce 1 second delay. This is actually impossible to do it sequentially, so this is why we do a sort of looping. We need to do a loop where we can keep repeating the execution till we reach to the 1 million times of execution. Okay, so let's do a loop within the subroutine. Alright, so let's say we need a no operation, and this is usually the easiest or the simplest instruction, no, and then we need to define decrement file, decrement file, skip F0, What do we need to do? So we need to define a variable. So let's go to the C block. All right. So let's define a C block where we will have some variable 0x70, and this is NC. Now we have, let's call C1. Now if you notice that we should have a variable here. Let's call it right now C1, and have F, and we have a loop go to loop. Now we will have a loop that it's keep running till we reached 1 million. But if you notice that the internal loop will have one cycle, another one cycle here, that's 2. The decrement will be 1 also, and then the go-to will have 2 cycles. That means as an overall we have 5. So if we have a continuous loop that has 5 cycles, so then we will divide the 1 million divide by 5. That will equal 200,000. So which means we need to have 200,000 times to run this loop instead of 1 million. Okay, which means that C1 must be 200,000, which is in PIC the maximum number for the register is 255. That means we cannot make C1 as 200,000. So the first thing is we need to put, say, move L. So move LW. We need to put a decimal number here for C, and then we say move WF C1. Okay. So now, if you notice at the code, we have a loop, and C will be fed up with a certain number, and then once we go inside the loop, it will keep running within the loop until C becomes 0. Then it will quit. Now we need to know how much C. What's the value of C? Well, as you know that the register is the range of the register is from 0 to 255, but since we are dealing with zeros, like you see here, if we divide by 255, we'll get some decimals. So basically we need to divide by 250. That means 200,000 divide by 250. That will equal, let me just calculate that. Okay, so 200,000 divided by 250, that's 800, which means we need another variable also to divide by 250. Let's divide by 200. So if we 800 divide by 200, that's equal 4, which means that we should have 3 variables. The first variable is C1 should be 250, and then the second variable will be 200, and the third variable will be 4. So if we multiply 250 times 200 times 4, we'll get 200,000. And then we have 5 here that will get 1 million. So if we define C2, then C3. Okay, so we said that C1 has to be 250. Okay, so now if you look at the, just zoom it a little bit. Okay, let me just put this down. Now if you look at the delay, so basically we feed C1 with 250 and it should keep running 250 times. Time is 5, which is 1250 times. So we need to have another loop where we can move LW decimal 200, then move WF C2. Okay, so this is the second variable for C2. Now we need to have a loop here. Let's call it loop 1. Let's call it loop 2. Loop 2 because it's C2, and we need to do a decrement file skip F0 C2 comma F, then go to loop 2. Okay, so what will happen that in loop 2 basically we will feed C2 with 200 and then we feed C1 with 250, and the internal loop will keep going till the C1 becomes 0. Then it will go to the C2 and it will decrement by 1. If it's not 0, it will go back and it will go back and feed up C2 again. It will keep running until C2, and I guess it will feed up C1 again with 250. Let me just double check this. So this is the loop. Go to loop. If it's 0, it will jump here. Then decrement is not 0. It will go to loop 2. I think it should go to loop 1. This is wrong. It should be here. Okay, I did a mistake. Basically the loop 2 will feed C1 again. Now we have another loop for move LW decimal, which we mentioned before. C3 is gonna be 4. Okay, so now move WF C3. Now also we need to decrement C4, decrement F skip 0 C4 and return it to C4 again, and then we have go to loop 3. Now go to loop 3 will feed the 200 C2, so we need to put it here, loop 3. So if you notice that C3 will be feeded only 4 times once. There is no loops. C2 will be feeded 4 times because it's inside the loop 3, and C3 and C1 will be feeded 200 times based on the loop 2. So this is how it goes. Now we can proceed, but let me just do a testing for the delay. Let me just write the code. So basically we need to have now we have bank select trace A or B or C. Then we need to make clear F trace C. So all trace C is an output. Now we need to bank select port A, bank select. Alright, now in port A, what do we need to do? Let me just get back to the exercise. So we need to display, put a value in port C, then in pin number bit number 0, then change it into 1. So we keep doing it this way. This would be simple. Okay. So now we need to do move LW binary 00000001. That's a binary, and then we put it to move WF port C. Then we call the delay 1 second. Then what do we do again? We can do something like that. We can do move LW. This is as simple as that, binary. Actually, we don't need to do an XOR. So basically 0000010, and move WF port C. Then this would be in a loop. It's called the loop X, and then we have go to X. This should be done. Let me just compile it and see if there is any problem. So as you see that we have a subroutine for the delay, and we call it here. Alright, let me just debug it. Build. Oh, a lot of errors. What's going on? Let me see. I don't necessarily big problem. See this one. Decrement F skip 0. Symbol not previously C4. Yeah, should be C3. Okay. Return. This is return. All right. Now let me just build it again. Let me just build it again. What's wrong? Still we have errors. Okay, alright. So this one, oh yeah, it has to be commented. Okay, let me just put it down. Alright. I think now we are good. Just do it again. Yeah, so it's all right now. It's fine. Okay, before we do any kind of simulation, let's first test the delay. See, is it 1 second or not? First of all, we need to go to the properties, and we need to go to the simulator to check that the instruction frequency is 1 megahertz. That means the clock frequency is 4 mega. Okay, this is good. So we need to test the delay. There are two ways of testing the delays. Let me just show where we can test it. We go to the debugging, I guess, and go to the stopwatch. Stopwatch allows us to see the execution time. So there is two ways to do that. Usually I do it this way. So basically this is the call delay. This is where we call the delay, and this is when we return back from the delay. So I put a 2 breakpoint, and I need to run the program. So let me just run it. Alright, so if you see, let me just reset it, pause, reset. So go here. So basically this is the starting point after the ORG, and then if we run it, it will stop in the call delay. If you see that, if you look at the stopwatch, the execution time from bank selectress A up to here is 7 microseconds. So I can introduce another one right there at the beginning of the call, and then I go to debug and run again. This will show us it's 1.003221 second, which is almost 1 second. Alright, this is good. We can do it other way. We just reset it again, and instead of put them here, we can put them inside the delay. So we can put breakpoint here and the breakpoint at the return, and then we run the stopwatch. We have another stopwatch. Let me just run it again. See, it's 1003217. So our calculations looks good. Now let's put a variable. Let me just delete the variables here, and I need to put port C as an output variable. New watch. Alright, and let me just remove the delay and just run it and see how it changes. Continue. So this should change one. I don't see any changes. Why? Okay, give me a sec. Pause. Reset. Let me just put a breakpoint here, and let's just run it and see. 0. Please wait. Why? Please wait. Okay, let me just pause it. Reset. Let me just put it this way, here and there. Alright, now let's run it. Now this is 0. See, it keeps switching, yeah, from 0 1 0 1. Yeah, see here, changing every 1 second. Okay, so that's it for today. I hope you enjoy the video. Bye bye.